In this lecture, we continue our discussion on approximate methods for solving scattering problems. So, if you recall, the earlier problems we solved without scattering were much simpler, because we could use simple exponential kernel approximation to convert an integral differential equation to a differential equation. But when we include scattering, the problem gets complicated by one order of magnitude, because a ray traveling in any one direction is linked to rays traveling in all other direction through the scattering process. So, in scattering problems, you have to worry about how intensity varies with angle. And if you recall, our intensity I prime is a function both theta and phi. So, this is the azimuth angle, and if you recall that we did not pay a lot of attention to the importance of angular variation in the case of problems involving absorption and emission. In most cases, we were able to make the approximation of diffuse isotropic emission, and that made the problem much simpler. So, the angular variation was accounted through exponential kernel approximation, which turned out to be quite adequate to deal with problems involving emission and absorption. But when it comes to scattering, these problems cannot be ignored. The angular variation is a critical factor in the case of scattering problems, and you need to carefully account for the direction in which the rays are going. Now, in order to explain how scattering problems are dealt with, we take the simplest example of the two-stream method, which we had discussed earlier, and we will continue this discussion today. So, what you are doing is you are essentially converting a problem which involves multiple directions to essentially two main directions, up and down, and you thereby try to simplify the complexity of the original problem. So, one direct way is to look at azimuthally averaged intensity. That is, you define an I, a function of mu, that is cos theta, as 1 over 2 pi 0 to 2 pi I prime of both mu and phi d phi. So, you average the intensity over the azimuth angle, this direction, and only account for the zenith angle. So, this refers to zenith angle, and this refers to azimuth angle. So, we average over azimuth angle, because in most cases the azimuthal variation is not that important as variation with zenith. For example, take the example of direct solar radiation impinging on a surface. So, the variation with azimuth angle is not as critical as the variation with zenith angle. So, that is the purpose. Once you do that, the basic problem in scattering, neglecting emission, boils down to writing a simple equation mu di by d, tau the optical depth, I, which is now function only of mu, not mu and phi, minus this single scattering albedo minus 1 to plus 1, the probability phase function, which depends on mu and mu prime, and I of mu prime d mu prime. So, let me just, so this is I so this is a simplified form of the radiative transfer equation, in which we have ignored the or average over all azimuth angle. So, that we only account for the zenith angle variation. Now, in the two-stream approximation, you have very simple assumption that I as function of mu is written as equal to two values, I up when mu is greater than 0 and equal to I down when mu is less than 0. So, after averaging over all azimuth angle, you are making a further approximation that the intensity is not varying with mu in the upper and the lower hemisphere, but the intensity upwards and downwards are not same. So, you want to fundamentally account for the fact that intensity depends on whether it is going up or going down, but within each hemisphere we are ignoring the now this can be illustrated by a picture here, which you will see now. So, we are going to have a simple model in which the upward and the downward hemispheres are, this is a simple model in which in the upper hemisphere intensity is independent of angle, and in the downward hemisphere also independent of angle, and you have only two values, I up and I down. Okay. So, that is the whole so, you are going to do that integration here shown as follows. So, everything simplifies in terms of I up and I down, or I out and I in. So, once you do that, the previous equation now becomes very simple. So, you now write the equation for I up and I down, and we will illustrate that now by showing that mu d I up d tau is equal to I up minus single scattering albedo by 2, 0 to 1 the scattering phase function, which is now function only of mu and not of phi, and so you are doing two integrations, one from 0 to 1 and one 0 to minus 1. we write this phase function of mu and mu prime I, this is now down into d mu prime. Okay. And so, what you have done here is that the intensity in the upward direction depends on what is already in the upward direction, and times the radiation scattered in the upward direction by particles from radiation traveling upwards, and also radiation which is scattered upwards from the downward going radiation. So, both these are accounted for in this calculation. And the advantage is, since we are assuming that I up and I down are independent of angle, we are going to take it out of the integration. So, then we are left with a simplified equation we are taking the I out of the integration because of the constant by our assumption. So, we will get a simple integration of the phase function Now, since you are going to encounter these integrals quite often, it is useful to define a B of mu as half 0 to 1 P mu mu prime d mu prime. And this represents the fraction of radiation that is scattered into the opposite hemisphere. Okay. So, it shows a ray travelling in direction mu prime, how much of it is going in the opposite hemisphere due to scattering. So, once we make this simplification, the final equation now for intensity upwards as a function of tau is given as I upwards minus single scattering albedo into 1 minus B into I upwards minus omega into B into I downwards. So, we have made the equation symbolically very simple. Now, we can integrate the equation over mu above equation, and so the function will become much more simple. So, when you do that and we define B bar, average value of B as 0 to 1 B of mu d mu. Okay. So, in each hemisphere this quantity will be defined. So, if we do all that, finally, we have a very simple equation minus half d I upwards by d tau equals 1 minus omega I up plus omega into b bar into I up minus I down. So, by all these approximations, we have reduced the calculation of the intensity going upwards in terms of just two parameters, the single scattering albedo and the mean backscatter fraction. Okay. So, remember that since there is a downward intensity coming here, you need two equations. Let me write down the two equations now, which we have to solve for. One is what I already wrote, and I will repeat that. Now, since this is an unknown term here, we have to write the equation for the downward intensity. And this will come out as 1 minus omega I downwards minus omega b bar into I up minus I down. So, we have two coupled equations, two coupled ordinary differential equation for the intensity upwards and downwards, and there are only two parameters of interest here. One is single scattering albedo, another was b bar, the mean back scatter fraction. Now, this quantity, which is the quantity which we call mean back scatter fraction, is a quantity that is related to a quantity which we call as the asymmetry parameter, which is defined earlier lectures. If you recall, when you talk about Rayleigh and mean scattering, we clearly identified a quantity called G, and the quantity G was nothing but 1 over 4 pi 0 to 4 pi p, the phase function of theta and phi cos theta do mu. This was the asymmetry parameter, and one must recognize that the asymmetry parameter and the backscatter fraction must have a connection. Now, the way we have defined the backscatter fraction, it is connected to the asymmetry parameter that we defined earlier as follows. Approximately, we can say that so if you recall in our earlier discussion, when G was 0, you had a isotropic scattering. So, it is equivalent to mean backscatter fraction of half, because if there is isotropic scattering, then the amount scattered upwards and downwards will be same. Similarly, when G equals 1, when there is only forward scattering. So, let me put this out clearly. So, when G is 0, you have isotropic scattering, and hence B half has to be equal to half. On the other hand, when G equals 1, you have only forward scattering, then B delta has to be 0, because there is a backscatter fraction. If everything is scattered forward, the backscatter fraction is 0. Similarly, when everything is backward scattered, B delta has to be equal to 1. So, the relation between G and B should be simple. Now, if you convert everything in terms of G, which is our new parameter, we can write a new set of equation in terms of G instead of B. Is only a transformation of symbols here. So, this is a result which clearly shows that if there is only forward scattering and no backward scattering and G equals 1, the second term will drop out, because then there will be no connection with the downward intensity contributing to the upward intensity. On the other hand, if there is only backward scattering and G is minus 1, this will become 1, and this term will cancel out and we will have 1 minus omega I downwards. So, what it is saying that, let me write down so that you appreciate this. So, when G equals 0, you have a simple equation which we have dealt with earlier. This problem has been solved earlier. This is isotropic scattering. Now, if G equals 1, this term drops out. You have half d upwards d tau depending only on this parameter, and if G is minus 1, minus 1 and minus 1 is plus 2 by 2 1, and this will cancel with that, and you will have 1 over half d upwards d tau will be equal to 1 minus omega I downwards. So, because G is minus 1, minus 1 minus 1 2, this omega, it will cancel with this omega, this will cancel with this. So, we are left with 1 minus omega term here and so this omega by 2 here will add up to this and you will get the following answer. And this result clearly shows in the second case that the upward scattering here depends only on downward scattering, because everything is back scattered. Here the upper scattering depends only on the upward intensity, because there is no backward scattering. Now, let us write down the two equations that govern this problem in terms of G before we solve it. And the first equation is what I wrote earlier. And the second equation for the downward intensity, which is can be written down by inspection because of the symmetry of the problem. So, we have two equations in two unknowns, there is I up and I down in terms of two parameters, the single scattering albedo and the asymmetry parameter. We can make this problem little more interesting, and we can combine these two equations, and with a slight manipulation we will get this equation. So, you can see that we have an equation for the essentially the mean of the upward and downward intensities in terms of the asymmetry parameter and the single scattering albedo, and one can derive a similar equation for the difference between the two. They look quite similar. So, we can solve the equation fairly easily. So, the solution of the above equation, a part of it we have done earlier when we dealt with isotropic scattering. Now, we are dealing with scattering which is not isotropic, because there is an asymmetry parameter which is not equal to 0. So, solution to this problem is I up plus I down is equal to some constant alpha e to the power of gamma tau plus some other constant beta e to the power of minus gamma tau, okay, and a similar expression for I up minus I down. So, in general you can write I up is equal to a e to the power of gamma tau plus b e to the power of minus gamma tau, while I down can be written as c e to the power of gamma tau plus d e to the power of minus gamma tau. And you can connect the two of these constants here, because they are not completely independent. And finally, we will connect everything to the total reflectivity layer called total albedo, called R infinity. So, we will define that quantity R infinity now for convenience, and we need now of course to solve this equation, we need a boundary condition, and the boundary condition that we will say that downward intensity that is coming in, let us say solar radiation, is I0, and at the bottom the total optical depth. So, we have a layer with tau equals 0, tau equals tau star, and this is the incoming radiation, and this surface is perfectly non-reflecting. So, the upward intensity of the bottom surface is 0. So, this is the simplest case that we can visualize. And so, if you solve this equation with these boundary conditions, we will get the following expression for upward and downward intensities. First, let us write the upward intensity. As a function of the optical depth, and we define parameter R infinity, which we will define soon. So, one is exponentially increasing, another one decreasing term. Here now we have introduced two parameters. We should define what these parameters are. One is R infinity, and we will understand the meaning of the symbol very soon. Now, you can see that there is some kind of total reflectivity of a thick medium, because when omega 1 is 1, this quantity becomes 1. So, when the single scattering albedo is 1, everything is reflected, and when omega is 0, this goes to 0. So, this is essentially a parameter related to total reflectivity of the medium, which we will highlight. And gamma the parameter that comes in the solution is related to the single scattering albedo and the asymmetry parameter. So, we have been able to obtain the upward intensity for a given I0, the downward intensity, in terms of this parameter R infinity, and this parameter gamma, and all of them are connected only to two factors which control the reflectivity in a scattering medium, which is the single scattering albedo, which tells you what fraction of the radiation is scattered as compared to the radiation is both scattered and absorbed. Okay. So, omega tends to 1, you have a very highly scattering medium, and if omega tends to 0, we have a highly absorbing medium. And G, the asymmetry parameter, tells you something about the direction in which the scattering occurs. If the scattering occurs equally in all direction, then G is 0, and we have isotropic scattering, which we had dealt with earlier. On the other hand, if the scattering is predominantly in the forward direction, then G tends to +1, while if scattering is predominantly in the backward direction, the G tends to -1. And so, this is the main quantity of interest, and if we define, and we have defined albedo before also, is the ratio of upward intensity by downward intensity, and this can be shown in this case to be nothing but R infinity. Okay. And so, albedo of the semi infinite cloud is R infinity, that is a quantity of great relevance, for example, in understanding cloud physics and quantity like that. Okay. Now, given the information, we can also calculate the net heating rate. The net heating rate will be nothing but pi times I up by I down, and this is of course a quantity of great interest in calculating the heating of the layer or an atmosphere. Now, let us take a special case of a non-absorbing cloud, that is, we set omega equal to 1, special case. So, it is essentially a non-absorbing or purely scattering layer. So, in which case our problem for upward intensity becomes nothing but I 0 into 1 minus G into tau star minus tau divided by so, in this simple situation where there is no absorption, the upward intensity depends only on the asymmetry parameter and the optical thickness. So, you can see that in this case the albedo, which is the ratio of the upward downward intensity R, will be nothing but, this can be calculated now. So, R will come out as the reflectivity of albedo as 1 minus G into tau star by 1 plus 1 minus G into tau star. So, this is a very simple result, and you can see again that if G equals 1, if everything is scattered in the forward direction, R has to be 0. This is understood from the definition of G, and if G equals to minus 1, everything is back scattered, that becomes 2, this becomes 2. So, R becomes 2 tau star by 1 plus 2 tau star, and of course, in the limit as tau star tends to infinity or becomes very large rather, R has to tend to 1. So, that is quite simple. And the other case where you have isotropic scattering, R becomes tau star by 1 plus tau star. So, we clearly get a simple idea of what happens there is forward scattering, what happens when there is backward scattering, and what happens with the isotropic scattering. And you can see typically that in the case of backward scattering, very often the reflectivity can be twice that of the isotropic scattering, especially when the optical length is small. But if the optical length is very large, then it does not really matter. If the optical length is very large, in both cases R tends to 1. So, what is worth understanding is that if a layer has a large optical depth, we are talking about 10 or about 10, then it does not really matter whether the scattering is isotropic or non-isotropic. The reflectivity is around the same value, 1. So, this insights we are getting fairly easily. We can also define a transmittance, which is also useful for many calculation. So, we will write down the transmittance. So, both reflectivity or albedo and transmittance are quantities of great relevance in practical application. So, the amount of radiant transmittance is 1 by 1 plus 1 minus g into tau star for a non-absorbing layer. And again you see that if g equal to 0, you have isotropic scattering, tau is nothing but, I will call the transmittance a different notation, because we do not want to t. So, transmittance Tr. So, transmittance tends to 1 plus 1 by tau star, then g equal to 1, that is forward scattering, then transmittance is equal to 1, not surprising, all the radiation transmitted in the forward direction, there is no absorption. So, you must have equal to 1, and when g equals minus 1, you have transmittance is equal to 1 by 1 plus 2 tau star. So, quite clearly when there is backward scattering, the amount of radiation that is coming in the forward direction is much smaller than when there is forward scattering. And as a matter of fact, in the limit of very high optical depth, high tau star, the transmittance can go to 0 if there is backward scattering. So, this simple analysis of a layer of non-absorbing particles has provided a general insight about the nature of albedo and transmittance in a very simple context. And what has to be kept in mind in the analysis is that if the only quantity of interest in a given application is the transmittance or albedo, and there is not much interest in the angular dependence of these quantities, then the kind of analysis we have done here is quite adequate. But if you need further information on the dependence of albedo or transmittance on the how it depends on angle, then this simple analysis is not useful. This simple analysis is azimuthally averaged and finally also averaged over all angles, and our focus only was on up and down. This is useful for many applications which are concerned with fluxes and overall hemispherically average quantities, but if you are interested in quantities which depend on angle, then the analysis done so far is not adequate. So, one needs to go to a more sophisticated model which accounts for the variation of intensity with angle, which we have ignored so far. So, let us see the kind of approximations that we need to make when the intensity is a function of angle. Once more, we will ignore the dependence on the azimuth, but first we will write down the equation with the azimuth angle explicitly indicated, so that you understand. So, the general problem now is both angular dependence explicitly there, and the pure scattering problem we are dealing with. This is a scattering phase function into the intensity, it depends on so this is a general problem of scattering. We neglected the emission term in this analysis. Now, the most rigorous way of doing this problem is to expand I, which depends on the optical depth, the zenith angle and the azimuth angle, in terms of spherical harmonics. So, you have I of m, which depends on now tau and mu, cos of m, some space direction minus phi. So, essentially, instead of assuming things are independent of the azimuth angle, which was the earlier approach we took, now we explicitly want to account for the azimuthal dependence of intensity through a cosine expansion, a Fourier expansion, and then in this case m is equal 0 represent the earlier result, the azimuth average. So, if you want to go beyond azimuth average, then this kind of expansion is called for. Then this function p, which is our phase function, which really depends on the angle mu phi and also the angle mu prime and phi prime. Now, this has been expanded in terms of m equals 0 to n as earlier, and then legendary polynomial will come in now. These are constants which we have to evaluate. These are the legendary polynomials which we will show what they are. So, these are the legendary polynomials. Are the appropriate basis functions for problems in radiation heat transfer. One can show that they are the most optimal choice. You could make other choices, but they will not converge or be as accurate as these functions. And so, let us look at how these functions look like. See, these functions were discussed earlier. So, this is example of the legendary polynomials of order 1, 2, 3, 4, and you can see that the first polynomial is a linear function, the second is a quadratic, and the third is a higher order, and so on. So, these are simple algebraic functions which are optimal for this problem, and if you want to further know what these look like, P 0 x is 1, P 1 x is x, and so on. And so, these polynomials are the ones which are used in many of the problems of this kind. So, once we have used this polynomials in our analysis, then the equation of rate transfer now becomes much simpler, and let me write down what equation we get. We will get equation for the I m now, because everything expands in terms of spherical harmonics. So, we removed the phi dependence through m, and now it depends only at tau and mu as before, but now we are accounting for azimuth variation, which we had not done earlier. And here inside now the integral over all azimuth angle. So, the integration over the azimuth angle is now has been done. So, we have now n plus 1 equations. That is, I am going from 0 to n. So, we have n plus 1 equations in n plus 1 unknowns. And the m equals 0 case is what we had done earlier, that is the azimuthally averaged quantity. So, that was a simple problem which we performed earlier in this lecture. Now, we go on to something more complicated, which is the now so m equals 0 is the azimuthally averaged quantity, which we have dealt with in the early part of the lecture. Now, we want to do something more, and so we adopt the so called Eddington method. So, in the Eddington method, we do not assume intensity is uniform in the two hemispheres. We allow for the intensity to vary, and the simple assumption that was proposed by Eddington is that I 0 varies as I 1 I 0 plus I 1 mu. So, essentially is varying the intensity to vary in the upward and the downward directions, and on account of this assumption, the phase function also is simplified now. It comes with 1 plus in terms of the asymmetry parameter. So, we have now a simple equation for I 0 and I 1. So, substitute this all in the equation that is given earlier. Now, we will get two coupled equations for I 1 which is 3 into 1 minus omega I 0, and this will be 1 minus omega g into I 1. So, we can eliminate I1 from these equations and you will get a single equation for I0, which is very similar to what we had derived earlier for the azimuthally averaged case. So, this analysis shows that both the very simple analysis done early in the lecture and the Eddington method, which is little more generalized intensity, which is dependent on angle, lead to very similar equations for I0. And these can be solved, and the solutions you will get will be similar to what we got earlier, and this will be continued in the next lecture.